Well, good evening, everyone. Welcome to the April 2016 edition of our Big Bear Valley Astronomical Society's virtual lecture series. I must apologize, it's been a hectic day and I haven't had a chance to think about an introduction here, so I'm really winging it. I think you're going to be in for quite a treat tonight. This is a topic. Well, let me back up. A couple of years ago, actually, I was talking to an ex-prof of mine, and who's a variable star type, and suddenly I got interested in the thought of asking him, gee, are there ever pulsating variable stars that can fall into and be pumped by the orbital period of in a close binary? And I was assured, no, this cannot happen. So, of course, after talking to him, I went on the internet and started looking around, and I came across some interesting papers that actually these things, not only do they exist, but they're being found now, and the Kepler Space Telescope, along with all the transiting exoplanets that it's found, has come across a few of these things. And one paper in particular stood out to me, KOI-54, the Kepler discovery of tidally excited pulsations and brightenings in a highly eccentric binary. I read the paper, excellent paper. I was just fascinated by it. Then I found the first author that was just down the hill from us at San Diego State, Dr. William Welsh. So I started pestering after him for quite a while, and I figured either at some point he would acquiesce and give a talk to us, or I'd get a restraining order. Instead, I broke him down and he agreed to give a talk, and we finally got that organized for tonight. Bill Welsh is an associate professor of astronomy at San Diego State, where he's been since the year 2000. He received his PhD from Ohio State in 1993 and is currently a Kepler participating scientist. He's really more of a exoplanet, transiting exoplanet kind of guy. But when going through the Kepler data, they found this fascinating binary star, did some analysis of it, and wrote that paper, which leads us to tonight. So without any more of my rambling here, why don't we just welcome Dr. Bill Welsh.
Thank you for that introduction. It was actually, I was quite honored that actually someone read that paper. Being an exoplanet person, that's where a lot of time and interest is spent. So this was sort of a side project, and it was one of the more difficult projects I've ever done. And the number of people who read the paper were very minuscule. And so when I heard someone was interested in it, I was like, fantastic, let's put together a public talk and see if we can enjoy ourselves for an hour here. Okay. Are we okay with the slides, the video, and everything?
Yeah, I'm on slide 1 here, your introduction slide. Your audio is chopping out just a little bit. I don't know if you're talking too close or too far away or what, but...
Okay, I'm not sure.
That sounds fine there now.
Okay. Okay, would it be possible to see my slides? Because it's a little difficult to know where I'm in. All right. Great, thank you.
You must be overdriving that.
Okay, so let me just start off by thanking many of the collaborators I've had, in particular Jerry O'Rose here at San Diego State, my co-conspirator in many projects. Ron Gillowitz, who's actually the one who pointed out this object to me, and he started the research on this and threw up his hands and offered it to me, and I accepted and time ago that. And then Kelly Hamilton, in more recent years, she's a graduate student just finishing up her PhD. She's very interested in these pulsating binary stars. And so it's been a pleasure to talk with her because it's her field, and she's really pushing the envelope. She's carrying the torch on with us. Okay, so let's go on with the next slide. So, my very brief introduction. I know you know about the Kepler mission, so let me just not dwell too much on this. But Kepler was designed to find transiting exoplanets, and in order to do that, it had very high precision, and it looked at the same stars for a long time. And this allowed it to be a fantastic instrument for all kinds of stellar astronomy, things like astroseismology, pulsating stars, eclipsing binary stars, variable stars of all sorts, in addition to finding transits. In fact, right now, the Kepler mission has formally ended, but it is now working as the K2 mission, and it is just about to start, or I guess it started this week, a campaign to do gravitational microlensing for planets. So we're hoping some good things come from that. Okay, next slide, please. So it was launched in 2009, and unfortunately, the reaction wheel on the telescope, the wheels came off the rails, and the telescope kind of ended its mission a little bit prematurely. It did the main things it was supposed to do, but there was so much more it could have done, and it ended in 2013 after about 4 years. Next slide, please. So just by comparison, there's Kepler in the middle, the Hubble Space Telescope you will know about on the right, and for scale, a person on the left. The Kepler is only about a 1 meter telescope, a Schmidt telescope. It's not gigantic by any means, but it's designed to do one thing and one thing only. And that allows it to really excel at the type of science it's doing. The Hubble and the James Webb telescope are designed to do many, many things. They're fully fledged observatories with hundreds of different types of observing modes. And so they're very much complex and complicated. And one would argue that for doing one thing and one thing only, they're not designed to do that. And so a smaller telescope like Kepler can do better than Hubble for this particular type of science. Next slide. So there's the focal plane, or there's the CCD camera. There are 42 different CCDs there. The field is so large that it actually is curved a little bit. Next slide. When you look up on the sky, or Kepler's looking up at the sky, you see that footprint of the 42 CCDs up there. So in the summer sky, Cygnus, Lyra, right between Deneb and Vega, up in the sky there is the Kepler field. Next slide. So that's a picture of the Kepler field. That's actual data from Kepler. Yep, dots that are the locations of 3 planets that were known prior to the launch of Kepler. And it's not a coincidence that 3 planets were known there. People knew Kepler was a big point. And so they were looking carefully at planets in this region, and 3 were found. Next slide. And at the end of the mission, that's the number of platforms. I'm sorry, the number of planets that Kepler has found.
I'll bet if he backed up, we could hear it better.
It's, again, your audio seems to be just a little bit choppy. It's been suggested maybe if you back off your mic a little bit.
Sure.
We'll try that. Thank you.
There you go.
All right, let's try this. Is this a little better?
Sounds good so far.
Okay. Okay, so the position of where planets are in the sky doesn't matter, so let's move to the next slide. And this is the much more interesting one. This is the radial, the size of the orbit of the planet, the orbital period along the x-axis, and the y-axis is the size of the planet. And the main thing to notice here, I guess there's 2 things. We could talk for a half hour about this one figure, but there's 2 main things I want to talk about. One is, at the top of the figure are the big planets, the Jupiter-sized planets. And the first thing you notice is there aren't as many Jupiter-sized planets as there are Neptune and Earth-sized planets. So that's pretty neat. It's telling you something about the distribution of the sizes of the planets. In fact, the most common type of planet is a planet that's in between the size of Earth and Neptune. And we have nothing like that in our solar system. So in that sense...
That's thought to be not a selection effect, but real?
For the Jupiter-sized planets, absolutely.
Well, I mean, for the primary size being between Earth and Neptune in size.
Right. So that's it's a mixture of the intrinsic sizes of planets and the fact that as you go below Earth size, it gets exceedingly difficult to find them. So when you're out at orbital periods of like 100 days, below Earth size, it's a very empty part of the plot there. Those are the hard planets to find. They're very difficult, and so that's a selection effect. The lower right part of that diagram is empty due to observational bias and difficulty. As you go to the left, it's easier, and as you go upwards, it's easier. So once you're at the left, you have orbital periods of a couple days. It probably is fairly complete, and the thought is, the distribution does seem to peak around 2 Earth radii. Okay, let's move on to the next one. And so just to summarize things, there's a whole bunch of planets that Kepler's found, about 1,000 of them, plus about 3,600 more candidate planets. And there's a mild distinction between the two. The 1,000 that we say are planets, well confirmed, well established. The other 3,600 are candidates, meaning we're about 85%, 90% confident they're planets, but not 100%. So we leave them as candidate planets for the time being. Okay, next slide. And then of particular interest are planets in the habitable zone, and there's about 300 of those. But if you have a Jupiter-sized planet in the habitable zone, it's not as interesting, so we want the small ones. It's about 50 of them, less than 2 Earth radii. And then the most important subset of all the planets, the gems of the Kepler mission, are these 18 that have a radius less than about 1¼ Earth radii and in the habitable zone. So these are the ones that are sucking up all the time, the telescope time, trying to follow up on these things. Now, unfortunately, the smaller the planet, the more difficult it is, and a lot of these are going to be false. They're not going to turn out to be planets of this size. We're going to find some calibration mistake or something's going on. So I would say of the numbers, 18, I wouldn't give it 90% confidence. It's going to be something less than that. Probably maybe half or even a quarter of that. Nevertheless, that's a good number to have, and it gives us something to work on now. These are the type of targets that will be followed up by James Webb. Okay, great. Next slide. This just shows you a little comparison of the sizes of the planets compared to Earth there, sort of up in the upper middle. And that they're around a variety of stars. There's some G stars, K stars, and N stars. Kepler was designed to find them around G-type stars, but really wanted more than 4 years of time to do that. So we've only got one, actually confirmed at this point. As we go down to the M stars, they're actually much easier to do, but there aren't many M stars, at least not that Kepler observed. So the sweet spot for Kepler were the K stars, and that's where we see most of these small habitable type planets. Okay, next slide. And then just to wrap this up, 2 more thoughts here. There is a very small planet that Kepler found, the Kepler 37b. It's about the size of the moon, and I think that's remarkable that we can find things that small. Next slide. And then finally, I can't finish up without talking a little bit about the stuff I like most, and that's planets around binary stars. So Kepler 16 was the first one of those found. Next slide. And then very quickly, right on the heels of that discovery, we found 2 more, Kepler 34 and 35. And with just a small subset of these, we know roughly how common they're going to be, and there's going to be lots and lots of this in the galaxy. They're not exceedingly rare flukes, they're actually fairly common. Next slide. The best of all these circumbinary planet systems is Kepler 47. There are 3 planets going around 2 stars. So it's a fun system, and we'll try to hope we can find more like Kepler 47. And next one. And just to wrap it up here, with the Kepler stuff, there are 10 circumbinary planets that we now know of. And the most recent one was announced in December of last year. We can move on now. All right. Here's kind of smaller terrestrial-sized circumbinary planet. We've got a dozen or close to 15 Jupiter-sized ones. Let's find some Earth-sized ones. Okay, next. All right, to get into the matter at hand here. So this is a light curve showing, well, let me just back up. This is the tidal page of the Astrophysical Journal paper that contained our discovery of the Kepler KOI-54 system. Next slide. And it's a really cute looking light curve. When I saw that, I was like, what? So actually go to the next slide. And I'll share this with you. When I plotted the data for the first time, I said, oh, I'm an idiot. I must have mixed up magnitude and fluxes, and it should be looking like this. It's just an eclipsing binary. And I double checked, and no, it really does go upwards. So next slide. It really does look like that. So what in the world is going on here? So we got these upward spikes about every 42 days. And if you zoom in a little bit more closely, the bottom panel shows one of those spikes. You see it's got this pretty nice sinusoidal oscillation going through there. And it continues right through the hump and back down again. And it's persistent the whole time. And if you look at each one of these brightens, you'll find that this oscillation repeats exactly in phase. So every one of these humps looks exactly like the ones. So what world was this? You've never seen anything like this. Next slide. So, the first thing you do is you do a literature search. See what's going on. So KOI-54, Kepler Object of Interest number 54, it's a bright star. It's a magnitude 8.3. That's the Kepler magnitude. So visual magnitude is similar, probably around 8 or so. So this is an HD star, 187091. So you look up HD 107091, see what's been published on it, and the answer is nothing. The last person to look at it, as far as we knew, was Henry Draper. And so it does have an effective temperature and a gravity, but we learned nothing from a literature search. So I guess the next return, hit return, next slide. Yeah, okay. So the first hypothesis that came up, this is what Ron Gilliland was working on before I came on board. He looked at this and said, what causes things to get brighter? And one of the answers is gravitational microlensing. And he thought, well, this is an A star. We know it's an A star from Henry Draper's work. But why would it get brighter? Well, if a black hole goes in front of it, if it's a black hole binary, and they're far enough apart that there's no mass transfer, they're not really affecting each other. But the gravitational field of the black hole will magnify the light of this A star. We'll get this light. So this was thought to be a microlensing event. So some X-ray observations were taken, and some high-energy data were taken, and absolutely nothing came up. It was completely empty. And then it was modeled in detail, and the brightening spike here just doesn't work. Microlensing really doesn't look like that. And the microlensing doesn't tell you anything about these pulsations. So it remained a mystery until we got a little bit more data. And that's the next slide. And this data here is really what cracked it. These are two spectra taken from McDonald Observatory by Bill Cochran. I think the lower one, was taken 2 days before the upper one. And so what do you see here? There's a little section of the spectrum around 5,400 angstroms, and you see absorption lines. Every single absorption line is actually a pair of absorption lines. So immediately, this is a binary star. And the second thing we know is from the strengths of the absorption lines, the two stars are very similar in brightness and very similar in characteristics. So just about every line is doubled. As we go up to the upper panel of the plot, the two lines are still there, but they're not separated as much. And this is due to the orbital motion of the binary. So the bottom panel, the two stars were moving at larger relative velocities with respect to each other. And in the upper panel, they were closer together in velocity. So the lines are starting to get blended. Next slide. This is the same type of observation. This was taken at the Keck High-Res by Jeff Marcy and company. And you see the same thing. Every set of absorption lines is doubled. And the pairs of lines are roughly equal in depth. So we have two A-type stars here. And whatever's going on, we have binary with two A-type stars. And this was really the clue that we needed to crack the system. Next slide. Okay, so jumping ahead a little bit, once we collected about a season's worth of data there, that's shown in the plot in the upper panel. And so these are the radial velocities, the doppler velocities of the two stars. And you can see you have this large swing, a cuspy thing, and it comes back again. So this is 2 orbital cycles here, or orbital cycle and a half. And it's a very, the cuspiness, rather than a nice sinusoid, tells you it's a very, very eccentric system. So we have a very eccentric system consisting of 2 A-type stars. And that's the clue that myself and Jerry Orloz needed to figure out what's going on. And independently, Bill Cochran also came up with it. These are 2 binary stars going around each other, and they are affecting each other as they get really close at periastral passage. The bottom panel there just shows you what the light curve is doing at those at the upper time. Next slide. Okay, so the eccentricity you get from the radial velocity curve is an eccentricity of about 0.83, which is very, very high. So these are very, very elliptical orbits. And they're going around each other. The orbits are not face-on, sorry, they're more face-on than head-on. They're nowhere near eclipsing. They're face-on orbits, and I can describe a little bit later on how we know that. But the main thing is they get close to each other, right? They get really close to each other. It's only a few stellar diameter apart. You could fit maybe 3 stars in between the 2 stars. That's how close they get. They go past each other, and they swing past each other very quickly. And as they get very close to each other, they gravitationally distort each other, and they also heat each other up because of their own radiation. So we get 2 effects going on. One is known as the ellipsoidal variation, and the other one is known as a reflection. And this has been known for 50 or 100 years in the binary star field, but never at this extreme. Okay, next slide. Okay, so let me explain what I mean by ellipsoidal variations. So imagine you have 2 stars going around each other. And if they're close enough that they gravitationally influence each other, they won't be spherical stars. They'll be squished and become ellipsoid, and they'll be squashed and sort of, well, the first order, they're squashed. The second order, they become a little bit more elliptical, and they sort of point towards each other. Now, because they're elliptical shape, as they go around each other, the light that you get from the 2 stars isn't constant. If there are 2 spherical stars going around each other and they're not eclipsing, we just get a constant line as a function of time. So this plot here is showing brightness versus time on the x-axis, or orbital phase. We're going to fold it around. So after every orbit, we come back and start again. So if the 2 stars are close to each other, they will tidally distort each other, become elliptical in shape, and as they go around each other, sometimes you sort of see them end on, and sometimes you see them sideways. And the difference, basically the area that you see of the stars, means you'll see them brighter when they're sideways than when they're sort of pole or face on. And so the light goes up and down a little bit. And this typically happens as the stars are coming towards and away from you, the quadrature phases. Now that's for a circular orbit. If you start to increase the eccentricity of the orbit, start to make them more elliptical, the shape of the light that you get, the light curve, distorts and changes a little bit. So if you hit return, we'll see a little distortion there, and that's an eccentricity of 0.1. So that's still pretty close to circular. Your eye can start to pick out the fact that it's not circular anymore, but it's nothing extreme. Next, as we start going up in eccentricity, though, we start to see the light curve changes quite dramatically. So what's happening is 2 things. The 2 humps are moving closer and closer to the periastral phase. So rather than being at the phase where it's halfway between the stars converging and going away, the eccentricity goes up. So everything happens when the stars are close together. So the 2 humps are migrating towards phase 1, which is by definition periastral in this figure, and the tidal distortion is getting bigger and bigger, so they're getting brighter and brighter. The distortion is getting more and more. They're getting less and less spherical. Hit return again, and you can see on this chart here they begin to go off scale. So, next slide. So here we are, rescale the whole thing again, and you can see this nice curve at the phase of periastral. The 2 stars are closest together get this significant brightening and then you don't see it anywhere else. Now, one of the really neat things about this is if you just look at the amount of brightening that you get, you can almost read off what the eccentricity is. So these are different eccentricities there, and when we look at KOI-54, we know that the brightening turns out to be about 1.007. So if you just kind of slide that across there and see one of these curves is close to 1.007, turns out it's an eccentricity of about 0.84. And that's almost exactly right. So you can actually get the eccentricity of an orbit simply from the light curve, without gradient velocities. So as far as this is the first time that's ever been done. And the reason this works is this brightening variation is exquisitely sensitive to how close the two stars are. And the closeness of the stars is very sensitive to what the eccentricity is. So if you change the eccentricity by only 10%, seen in this figure here, you get very significant change in brightening there. Okay, next slide. Now, another thing, which is the shape of this ellipsoidal distortion, the tidal distortion of the star, and how does the shape affect what you see? What is the brightness of the star? So it's going to depend on several things. The eccentricity is one of them, but let's lock the eccentricity down. Let's hold it fixed at 0.84 and see what other things can influence the shape of the light curve. So on the left is low inclination. This is an inclination where the system is only 5 degrees, meaning it's almost face-off. Two stars are going around each other, and you're sort of looking at them as they go around the sky this way. On the right-hand side, we're seeing a much higher inclination. Not enough to eclipse or anything like that, but a higher inclination. You can see these are the exact same model, but as viewed from a different angle, the shape of the light is quite different. Okay, next slide. Right. Let me just mention here the darker see here. So I mentioned as the stars get distorted, you see more of their area, and so it gives you a brightening. More of the stars in phases and other phases. So you might be asking, why is it darker as some phases? Well, it turns out when you distort a star and you squish it, and it becomes a more of a prolate or ellipsoidal shape, but the temperature is not going to be constant around the star. There's this thing called the gravity darkening effect. And that goes back to 1907. Van Zytel came up with this. It's a really neat effect. But the punchline is the surface temperature will be the same all around the star. And as the star rotates, different parts of it come into view, some parts are going to be darker than other parts. And when the darker part of the star is pointing towards you, and because it's not spherical, where you get two things. The darker part means you're getting less light, and that the star is not spherical, getting self-occultation of the star. The distorted part of the star is starting to block some of the other part of the star. The pointy end of the star is blocking the side of the star a little bit. So you do see these sharp dips and losses of light before you see the brightening there. Okay, next. So as we go on for different inclinations, you see different shapes here. You see a variety of different shapes. Depending upon the viewing angle, the inclination, and also just the rotation of the binary in space. What I mean by that is, what is the orientation of the ellipses? Are the ellipses pointed toward you sideways or what random angle in the sky? Next. And one more. So you can see that these shapes are very, very different. This is all the same binary system. It's all viewing dependent. Okay, let's go to the next slide there. Now, there are two parts here. I've been talking about the tidal part, the distortion, but there's another part too. That's the irradiation, or it's known as the reflection effect. As the two stars get close to each other, they heat each other up. Now, it's not significant. We're not talking about huge variations here, but it's about 100 degrees Kelvin. And that's enough to change the brightness of the star. So the hemispheres of the two stars facing each other momentarily get hotter and brighter. And as we're seeing those faces, goes up. So we can untangle the two components of the brightening, and there's two parts to it, the tidal part and then the radiation part shown as the dotted line. You don't see it here, but if you look very carefully, it's not symmetric. It's not symmetric around phase 0. And that helps you determine what is the orientation of the ellipse in space. Next. Okay, so we do the same thing now. This is the tidal distortion plus the radiation. The left-hand side is for low inclination. On the right-hand side, what we do is we just change the orientation of the orbit in space and see how very different light looks. The ellipses are arranged one way or arranged another way. So hit return there, and again, and one more. You can see there's a bunch of different shapes here. These are all the same binary stars, but what you would see depends very much on the orientation of the binary in the sky compared to your line of sight. Okay, next. All right, so here's our simulated model for KOI-54. We got two A stars going around. They're on extreme centric orbits, as you can see here. So most of this is drawn to scale. I think it's all drawn to scale. Oh, let's see if we can play that again.
There we go.
There we go, great. The upper right is light. The upper right panel shows the brightness. So at periastron they get really bright, and then not much happens when the two stars are far from each other. And the bottom right panel is the radial velocity curve. It's the exact same thing with the radial velocity, so you can see the custom nature there. Two stars go around each other. Well, this will actually stay again on another slide, so let's move on.
Okay.
I like that.
Okay, so that explains what's going on with the brightness. So that explains these 41.8 day brightness. Two stars in very centric orbits going around each other. When they get close together, they distort each other tightly, heat each other up, and you get this brightness. It looks very dramatic in this figure. That's because Kepler sensitivity is so remarkably exquisite. Kepler can measure things roughly at the 30 part per billion level. And here we're talking something like, getting close to 1%. So it looks huge. But in fact, you look at the y-axis there, this really is kind of a small potatoes thing. This was never seen around before we observed this because it's actually less than 1% effect. Okay, so that's the brightness. I haven't said anything about these oscillations here. It's also a very interesting part of the story, perhaps even more interesting. So let's move on. So a couple things to notice, a little bit of an aside about these different oscillations here. The one thing to notice when you look at the KOI-54 light curve, actually, can we back up for a second? Right, if you look in the upper half there, you see the band of black points there. And it kind of gets broad and narrow, then broad and narrow. And we're seeing what's known as a beat phenomenon. We're seeing an envelope of these pulsations that are kind of big at periastron where things get bright, and in between they get small again, and then they start getting brighter and smaller again. So next slide. So this is just showing exactly that. We have two oscillations that are very similar in period, very simple frequency. They beat against each other. And so the upper two oscillations there are two sine waves that are very similar in frequency. And if you simply add them up, you get the lower curve there. And you see this nice envelope where it's very small in the middle, and then it grows bigger, and then after a while it shrinks back down again. So we're seeing exactly that in KOI-54. Next. Let's see if you can hear anything there.
Okay, this is going to be on the laptop speakers, so let's be quiet here. Everybody hear that? Okay, I think everybody in here was able to hear that.
Yeah, great. Yeah, it's not the most exciting music. But you hear this whirring sound and you hear this kind of change in amplitude. That's the beating sound. So by looking at the light curve and hearing the sound, we're already getting the sense that there have got to be two periods in there not just one sine wave, but there's got to be two. They got to be close together in frequency to give us this beating pattern. Okay, next. So a quick little diversion about astroseismology, pulsation of stars. So here we've got a little tiny schematic Hubble diagram here, temperature on the left and spectral type on the bottom, OBA, FGKN thing. And we got temperatures there. And the dotted lines going off to the towards the upper right, that's the classical instability strip. And this is where stars that are slightly evolved off the main sequence will pulsate. And so the RR Lyrae variable stars and the Cepheid variable stars that you may have heard about, these wonderful stars for determining distances, live in this part of the HR diagram. Next. But it's there's a lot more going on there. So here's an HR diagram with a lot more things labeled on it. Towards the upper right, we do see the dashed lines there. That's the classical instability strip. As we get down towards the main sequence, there's a bunch of labels in there. There's this thing called Gamma Doradus, Gamma Dor, and then Delta Scuti. These are pulsating stars that are closer to the main sequence. And of course, off to the lower left, you get pulsating white dwarfs and that sort of thing. Okay, let's move on. Okay, so what we're seeing here are different modes of a very, very simplified version of pulsations of a hypothetical object here. And I guess the two things I want to point out is the one on the left is a radial pulsation. And what that really means is the radius of the star is changing. So the star is getting bigger, and then as it gets bigger, it gets redder, it cools off, and then now it's too cool, so it shrinks back down. As it contracts, it heats up, and it gets too hot, and so then it expands and cools down. So you get this cycling, the thermal cycling, getting bigger and smaller and bigger and smaller. So those are the Cepheid variables and the RR Lyraes and a lot of those variables that we use for distance scale things. That's the left-hand one. The one next to it is a mode that we don't observe because the center of mass is moving. And that does not happen. It's a violation, so we don't care about that one. The one after that is the one that we're more interested in. It's more similar to the type of binary as KOI-54. We're seeing the star gets squished. Now, the way to think about it is in this one, I just said squished. It looks like it's being compressed from the top and bottom. The more correct way to think about it, as the two stars go around each other, and periastral, they start to pull each other sort of at the equator. So rather than thinking about the stars getting squished from the poles, think of them being pulled out at the equator. So they get pulled out, gravitationally pulled out, and then as the stars leave periastral and move away, the star kind of goes back to its normal shape. So you get this oscillation, sort of the poles going in and the equator coming out. Okay, next slide. Now I don't want to get into stellar pulsations and astroseismology. It's too complicated for me. I like to work on planets, but I just wanted to give you a flavor of what's going on here. Typically, when you talk about oscillation modes, there are three numbers: N, L, and M. And N is the number of nodes you get interior to the star, so it's stuff underneath the surface. You can think of it as how many layers of up and down that you're getting inside the star. And then there's L and M. These are the number of azimuthal variations you get on the star. Next slide. And you can just imagine there's a rich variety of these spherical harmonics, all kinds of things you can get. The only one I want you to think about, though, is the one in the upper right. This is the L equals 2, N equals 0 mode. And what's happening here is the same as before. Imagine that the star is getting distorted at the equator, being pulled out at the equator and compressed at the poles. And that's the oscillation mode that we think KOI-54 is in. Okay, next. Okay, one last thing about oscillation, seismology, and all this stuff is there's a really neat theorem by this guy, Fourier, goes back to the 1800s, where almost any shape you can imagine can be decomposed or reconstructed, I should say. You can make any shape by just adding a bunch of sines and cosines together. You may need a lot of them, but as long as you have a whole bunch of sines and cosines, if you add them up in the right amplitudes and phases, you can make almost any arbitrary shape. So the upper panel up there shows you a oscillation of a variable star, let's say. And it's sort of sinusoidal, but not really, because it's much too flat on the inside. It really looks more like a sawtooth or a square wave. Not a square wave, but a sawtooth. It kind of goes up as a triangle, comes down, and goes up again. So it's not sinusoidal. But it turns out, with only 3 sinusoids, you can reproduce that upper panel. So the lower panel is showing you the 3 sinusoids that go into making the upper one. So you got the larger sinusoid, sort of the dashed line there. The longer dashed line is the next mode, and then the next frequency, I should say. And then there's a very small one, almost at 0, that you add together. All of those 3 added together will get you the upper one. So the point of this is you can get almost any shape you want by just adding together sines and cosines. Okay, next slide. All right, now this may or may not work so well. The idea here is to give you an idea of what a power spectrum is like. And power spectrum is a very useful tool in many fields of science and engineering. And we're going to see a couple of power spectrum in the next few slides. So I wanted to spend a minute kind of explaining what's going on here. So as I said, you can take any signal and break it down into a bunch of sines and cosines. And what is it about a sine or a sine wave that that tells you let me back. What is the information in the sine wave? What things do you need to specify a sine wave? And you need really the amplitude of the wave, you need its frequency, and you need its phase. Those are the only 3 things you need. And so a power spectrum will plot the amplitude and the frequency. The phase usually is not that important. The phase is important if you want to get details right about the shape. But the more of the information that's important is what frequencies are present and how strong are those frequencies. How strong is the amplitude? What's the power at that frequency? So this little cartoon here should be playing some notes, some musical notes. And on the left is the musical notes on some kind of scale, and on the musical notation. The right-hand side is trying to show you the strength of the signal versus the different frequencies. So there are 5 different frequencies plotted there. As you go to the right, that's higher and higher frequency. It turned out to be higher and higher pitch. On the y-axis is the amplitude, or how much power is in that signal. Now, unfortunately, this cartoon isn't the best in the sense that it looks like the amplitudes are dropping off very linearly. The lowest frequency one is a tall amplitude, then it gets smaller and smaller and smaller. But when you listen to this, it's not obvious that the amplitudes are any different. So if we click on it, we should be able to hear some notes here. And this little animation, whoops. I think if you click right on the animation itself. So the first one, harmonics. These are notes that are spaced regularly apart. This little example here is irregular spacing. It just doesn't sound as good to the ear.
Unfortunately, on my laptop, it's not very loud in here, but I think people could sort of hear that.
Yeah.
Okay, well that's okay, yeah. The idea is simply just to relate the fact that a power spectrum really shows you the strength of the different sinusoids that go into making up the signal. All right, let's go to the next slide. All right, so finally, here's the power spectrum of KOI-54. And so the spikes that are going up are telling you these are different sine waves that are carrying power in the signal. These are different sine waves that when you add these all together, you will get that shape that we saw earlier on from the oscillating heating light curve. Okay, so we've got some little spikes here, and we've got 2 big ones on the right there. The ones on the right turn out to be at frequencies near around 2¼ cycles per day. I don't like to think in frequency space, so I wrote down the periods up there. It's 11.15 and 11.03 hours. So the sine wave goes up and down in 11 hours. Now, there's two of them, and they're very close to each other. And that's what I mentioned earlier about the beating. This is what's causing the beating effect of the light curve. These two sinusoids being so close together are creating a beat, and so when you look at the light curve, you see the amplitude rise and it shrinks back down again, and it rises and shrinks back down again. Now, the fascinating thing about this is not that you've got stellar oscillations and they beat against each other. We've seen tons of this stuff. What's really cool about it is that this 11.15 and 11.03 hours turn out to be related to the period of the binary, the two stars going around each other. So it turns out these oscillations are exactly the 90th and 91st harmonic of the orbital period. So note the orbital period is about 42 days. If you take that and divide it by 90, you get one of those frequencies there, and if you divide it by 91, you get the other frequency there. So these oscillations are being driven by the binary star itself. They're not natural modes inside the star. A lot of stars naturally ring. The pulsating variables ring. The sun has vibrations of 3 to 5 minutes. These stars don't naturally vibrate. They're close to delta Scuti stars, so they might vibrate, but the delta Scuti variations would be at much, much higher frequencies. These are very low frequency variations for this type of star. So they shouldn't be there. But the fact that they're there means something is exciting the star, something is causing the star to oscillate. And it turns out it's this periastron passage. When the two stars go past each other, they gravitationally distort each other. And basically they give a little push, or a tug, I should say. Each star tugs on each other. And that will resonate with the star, and the star starts to ring at these harmonics of that orbital period. Okay, next slide. If we zoom in on those two there, we can see them separated there. Yeah, I guess nothing special about this, but they're cleanly separated there. Next slide. Okay, so the upper panel shows you the power spectrum. If we remove those two sine waves, so we know their frequencies, we know their amplitudes, we know their phases, take two sine waves like that, remove them from the data, what's left is the lower panel. And by doing that, we can now look at the lower amplitude frequencies in a little bit more detail. They show up a little bit nicer. And so there's labeled in there, it goes up to F12 or F13 or so. These are 13 or 14 different frequencies that are easily identifiable by eye. If you go and do this carefully, there's up to 30 that are easily measurable. And if you do it really, really carefully, there's about 100 of them. All right, next. Now, the upper panel up there, it shows that the two frequencies are the harmonics of the orbit, the 90th and the 91st harmonic of the orbit. So what about all these other spikes on the left? What are those? Well, can you hit return? So, turns out they are also harmonics of the orbital period. They're the 44th, the 40th, the 72nd, the 63rd, the 20th, so on and so forth. Almost all of these spikes here are integer fractions of the orbital period. Okay, next. And so here's a little table showing you, well, the frequencies and the amplitudes, the ratios of what they are compared to the orbit. So I guess if we go to the second to last column on the right, the closeness of that number to being an integer is telling you how close it is to being a harmonic. So you can see that the first four are perfect harmonics. As you go down a little bit, you can see some sort of small deviations, but they're pretty close to being exact multiples of the orbital frequency there.
Now, the ones that aren't perfect harmonics, is that, are they being modified by the natural resonance of the star, or is there something going on that pulls them off of it being a harmonic of the orbital resonance? Or orbital
Right. Good question. We'll come back to that in a second. If I don't answer that, bring it back up, okay? Okay, next. Okay, so finally we can put this all together. We've got our binary star model, that's shown in red there. We've got our pulsating star model, that's shown in green below, and in black is actual data from the Kepler mission. And it's a pretty good match. we got to be careful. What we really want to do is take the green and the red and add those together and compare that with the black. But we didn't do it in this figure. We'll do that in the next figure. Here, what I'm showing is simply the motion, the tidal distortion of the stars and brightening in red, and then the pulsations in green. And so it's very hard to see that the green plus red is not going to equal black. If you look really, really carefully, there are a couple of places where it doesn't match very, very well, but for the most part, it's pretty good. Okay, next. Okay, so here now is a real comparison with observations and data. The observations are in red. Sorry, the observations and the theory. Observations and data better match. Okay, so the observations are in red. The theoretical model is in black, and they match pretty darn well. What we're showing in green are the residuals. This is the difference between the two. You take one and subtract the other. And in order to see the variations, we multiplied that by a factor of 5. So we've expanded that 500%. So you can see the deviations from the difference between the data and the model that we came up with. Okay, next. Boring table of all the parameters here, but we measured lots of things about the stars, the radius, and the mass ratio, the temperatures, and rotations, and all that stuff. Let's move on. Okay, so is the deal here. So let's just kind of put it all together. KOI-54 was basically just a boring A star in the sky, a HD boring star. But it turns out it's a nearly face-on eccentric binary. As the two stars come past each other, they gravitationally distort each other and heat each other up. That's not too unusual, but it's not been seen to such an extent. But more interesting is that as the two stars go past each other, they excite oscillations in the stars. These are G-mode pulsations. G-mode is the gravity mode. These are deep inside the star, or they're deeper inside the star. They're not surface effects. And the G-modes are gravity modes. They're buoyancy modes. Things go up and down, and they're restored by gravity and buoyancy forces. That's in contrast to the pressure modes, which we're not seeing. Pressure modes are usually at much higher frequencies. So the 90th, 91st harmonics are there. They dominate, but there are at least 23 more that you can find. And if you push hard, we stopped at 30. We said, well, there's no point in this paper digging for the noise, but when we did our analysis, we did find up to 100 of them. And then, again, 100 is an arbitrary number. We stopped at 100 because we didn't, there was no point running the code to find 112. It just stopped. Okay, next. So that's to first order. That's the deal. That's what's going on with the two stars. But there are some really interesting questions here. Like first of all, which star is pulsating? And it turned out this is a very difficult question. We don't know. It could be one, or it could be the other, or it could be both. And why would be one and not the other? We can't answer that. The two stars are very similar. In that table that was there a few slides ago, with all the boring numbers in it, the two stars are very similar in mass and temperature and radius, but they're not exactly the same. So if one star is pulsating and the other isn't, it must have something to do with the stars. I mean, they're the same age, they're the same chemical composition. The only thing that really differs is their mass. And then the consequence of that slight difference in mass means a slight difference in temperature and radius. So if one is pulsating and the other isn't, it means something is happening that's exquisitely sensitive to the mass. Another thing that comes up is why is it the 90th and 91st harmonic? Why not the 22nd and 23rd or 180th and 181st? There's no answer to this. Probably the answer is, well, it's by chance, these are the ones that get excited. These are the modes interior to the star that are closest to being in resonance with the orbital period. That 41-day orbital period. If the orbital period were 31 days, it wouldn't be the 90th and 91st harmonic, it would be some other harmonic. another interesting question. If it's 90th, 91st harmonic, why not, and then there's the 42nd harmonic and the 56th and all the other stuff. Why aren't there higher harmonics? Why is it that gives you a sharp cutoff at 91? There's no 92, there's nothing higher than 91. And 91 is one of the strongest oscillations in the whole star. So there's something going on there that says we get up to 91 and no higher. Okay, now you ask about the pulsations that are not orbital harmonics. What are they? Well, they could be rotational. So when these stars rotate, and when you rotate, that's another periodicity, and then that periodicity could mix with the pulsation periods, and that could bring up a third period. We don't think it's rotational. Rotation usually will take a line and split it and into three, and then you can measure them, and so it's a symmetric splitting. We don't quite think it's rotational. Next slide. So here's that slide I showed you earlier, and the red arrows are showing you some of the spikes there that are not orbital harmonics. So these are not integer fractions of the orbital period. We don't think they're rotations. However, hit return. If you notice, if you take frequency 5 and frequency 6, add those together, you'll get frequency 2, exactly. So while F5 and F6 are not orbital harmonics, the sum is an orbital harmonic. And hit the slide again, return again. If you look at F6 and F8, and F8 and F9, those are also related to each other, the separations between them. So there's some funny things going on here, where the separations between peaks may not be orbital harmonics, but they might be related to orbital harmonics. So there's one thing that does create this besides rotation, and I think that's on the next slide. Sorry, okay, I'll come back to that. Yeah. And that is, if you have a lot of power at some modes, and a whole bunch of different modes, they can actually excite other modes. So one mode, if there's a lot of power in there, it becomes a little bit non-linear. It's not there's so much power in the mode that it sort of leaks out to harmonics of that mode, such that the sum of the two other frequencies add up to the original frequency. So in other words, in the upper panel, F5 and F6 would really be power leakage from F2. And that's, at this point, one of the best explanations for those other harmonics there. I'm sorry, for those other powers that are not orbital harmonics. Okay, next slide. So the paper was written in 2010, and that was using 1 year of Kepler data. Kepler lasted 4 years, so there's 4 times as much data. So we took a quick look after about 2 years to see, make sure we didn't mess up anything, the star was still pulsating. So let's go to the next slide. And what we did was simply take our model and don't do anything, just fast forward in time and see how it continued to match the future data. So the upper 2 panels there are what we based our model on. That was in the published paper. And the other panels on the bottom there are data that we did have at that time. And next slide. And this shows more. So this shows the next 2 years worth of data and how well our model continues to match the observations. So it's not perfect. If you look at the bottom slide there, in particular, you'll see some of the green points are above the average or the 0 line, and some are below. I have a pretty good idea of what's going on here, and it's not a deficiency of our model or the stars doing something funny. It's the calibration of the data. Kepler data is exquisitely good for finding planets, but on long timescales, it's not so good. It has a lot of drifts. Now, normally, if a star is drifting in brightness, it's an instrumental artifact, you don't care. Just get rid of it. You divide it out. But you can't divide it out for Kepler, for KOI-54, because every part of it is interesting. So let's imagine you have a planet, and every 50 days there's a transit. In between, you generally don't care what the star is doing. So if the star seems to be losing brightness and then gaining or has a little wiggle in there, we don't care. So you just really just normalize it out and throw it away or calibrate it out and don't worry about it. But for something like KOI-54, where something is always happening, it's always interesting, there's no place to say, well, you can just throw out the data and renormalize it. So it turned out to be tricky. And with these models here, all we did was fast forward in time. We didn't try and be clever or anything. We just wanted to see, is it ballpark correct? And I think the answer is, yeah, it's pretty good. If you want to spend another year and really slave away, you could do better. It's not clear how much more you would learn. So maybe, we'll get a student or something to do that, but I'm not interested at this point. Okay, next slide. Okay, so we've got some puzzles here, and one of the puzzles turns out to be, what's the masses of the stars? Now, in an eclipsing binary, it's easy to get the masses of the stars. The radial velocities gives you the mass ratios, and they give you the mass with respect to, well, modulated by the inclination angle. And if it's an eclipsing binary, then you know the two stars are eclipsing each other. You know what the inclination angle is. You get the masses exquisitely good. So the way we know masses of stars come from eclipsing binaries. But for KOI-54, it's almost the opposite of an eclipsing binary. It's face-on instead of being edge-on. And so there's a big difference here, and it kind of caught me by surprise, and all the people working on this, because we're so not used to working with stars that are face-on rather than edge-on. When a star is edge-on and they're going around each other, the velocity is modulated by the sine of the inclination angle, so sine of I. If the inclination is 90 degrees, the sine of 90 degrees is 1, and so you don't care. If you're a little bit off, and it's not 90 degrees, it's 89 degrees, the sine of 89 degrees is practically 1, and so you don't care. And you could be off by a couple of degrees, and the sine doesn't care, because you're at the peak of the sine curve, and it's flat up there. So if you're off a little bit from the peak, it doesn't matter, you're going to get the masses accurate to, much, much better than the first attempt. For KOI-54, we're down around 5 degrees. Our angle is 5 degrees. And the difference between the sine of 5 degrees and the sine of 6 degrees, when you cube it, because the mass goes as the sine cubed, it turns out to be a lot. It's not quite a factor of 2, but it's almost that. So if you get the inclination angle wrong a little bit, you get the masses completely wrong. And so the evolutionary state of the stars and the picture of do the stars have the correct radius for their mass and all that depends on knowing the mass. And knowing the mass turns out to be exquisitely dependent upon knowing that inclination. And how in the world do you get the inclination for something that's not eclipsing? Well, you get it from that periaspin brightening. So a lot relies on exactly the combination of eccentricity and the inclination to really, really match the data and pin that inclination angle down to better than a degree. And we're sort of at that. The precision is about a degree there, but the accuracy could be quite a bit off. Could be 2 or 3 times that. And that means a pretty significant effect on the masses there. Okay, so that's one thing we need to worry about. We can measure the data, after 4 years, we can go back and see, do the frequencies or the amplitudes of any of these sine waves change a little bit? That would be very interesting. To first order, the answer is no, but we haven't really, really looked carefully enough. Another thing that would be interesting is the period of the orbit, 41 point something days. We can actually measure that pretty precisely. And the question is, if you measure that very precisely, do you see the orbit evolving? Now, you might not expect that, but you could, with Kepler sensitivity, you could pick up this thing called apsidal motion, which is the slight rotation of the orientation of the ellipses in space. So because the stars are not spheres and because they're exchanging angular momentum with the orbit, their stars are spinning up, the orientations of the orbit in space can rotate a little bit. And if we could measure that, that can tell us a lot about the tidal dissipation of energy or the exchange of angular momentum inside the stars with the orbit. The other thing is, if the ellipses start to precess or change this apsidal motion, that could be due to the third star. There's nothing to say there isn't a third star in the system that's much less bright at maybe some long orbital period there. We don't see any evidence for that, But that would be something that would show up in the change in the periods, the P dot term there, a time derivative of the orbital period. Okay, next. Now, very quickly after our paper was published, there was this flurry of activity by some theorists trying to explain the pulsations and how you can get resonance, how orbital modulations, how the periastron passage can tidally excite pulsations inside the star. There are a couple papers on this. They're very technical, and basically one paper says this, the other paper says, no, that can't be right, and the other paper says, no, you're wrong, it's this. So at this point, I don't know. I really don't know why it's the 90th and 91st, and exactly the details of why some modes are excited and some aren't. Basically, it's this thing called this resonance locking mechanism where, sure, you can excite modes inside the star, right? So this 41-day period is going to make the star oscillate. At a period, the stars are not oscillating at 41 days, they're oscillating at 91 times faster than that. And why 91? Well, that's the mode that the star naturally wants to vibrate at. The way I think about it is, imagine you just have a guitar and you got the strings there, and you're not plucking the guitar, but you take the guitar body and maybe you just rub it with sandpaper or something. The strings will start to vibrate. And that's because they want to vibrate, and they will vibrate at the modes that they want to, irregardless of how you're exciting the modes with your stupid sandpaper on the guitar. So the star is resonating the star is vibrating at this 90th and 91st harmonic and all these other harmonics because that's what it wants to do. It would not do that if it wasn't excited by the periastron passage, by the other star kind of squeezing the star and forcing it to do that. Now, those are the papers in white there. What turned out to be very interesting is after we published our paper, it was pointed out to us that there was a paper in 1995 pointing out that you should have expected this. You should really, these sorts of oscillations and the brightenings were predicted back in 1995, and they showed something that looks very similar to what we observed. We got to be a little bit careful there. That paper from Kumar et al. Was about a star and a neutron star going around an A star or a B star, and tidally distorting it. So it's kind of a different scenario here. And what they predicted is not exactly what we see, but there are things in that paper that look remarkably like KOI-54. And then some observational papers came out. Susan Thompson and Kelly Hamilton have really led the show on these types of stars. Let's go to the next slide, and I'll show you what I mean here. This is that paper by Kumar, and in particular, the upper right panel looks remarkably like KOI-54. Now, we don't have the beating there. It's only one harmonic of the orbital frequency there, not two, so we don't see the beating effect, but that looks very much like KOI-54. The problem is the y-axis there is not brightness. If this was amplitude of the brightness of the star, this would be a remarkable match. This is actually the amplitude of the mode that's interior to the star, and by the time it gets to the surface, and what you observe is a complex convolution of various things. It doesn't look like that anymore. But at least they were pointing out that inside the star, there are modes that should oscillate, and it should look like that. And that is exactly what, well, it's almost exactly what KOI-54 looks like. All right, next slide. Going to some of the data here, very soon after our paper was published, Susan Thompson was looking at other Kepler data, and she found 17 more of these systems. She called them heartbeat stars. At first I didn't like that, and then I said, all right, it's okay, and now I've grown to hate that name. The reason is, if you had EKG and your heartbeat looked like that, you better run to the hospital. And the other thing, there's so many different shapes. So the heartbeat star, well, I don't know. But anyway, the name seems to have stuck, and people are calling it that. Next slide, please. All right, so as of now, There's actually quite a lot of these. Kelly Hamilton is one of the people really pushing this, along with other people working in the Kepler data, Susan Thompson and others. I think there's 183 of these now. 173 have been discovered by Kepler. These are stars that show this tidal distortion and brightening. That's what I mean by heartbeat stars. Of those, there are some that are intrinsically pulsating stars. A good fraction of stars pulsate, and so there's a good fraction of these. These typically are A-type stars, and A-type stars like to pulsate. And so about 50% of these naturally pulsate, independent of any tidal forcing. Next slide. Here's some examples of some stars that show tidal locking. These are the ones I think are more interesting. These are the ones where the oscillations are exactly in phase with the orbit of the two stars. So the other ones are, Kelly and Susan call them heartbeat stars, but I'm reserving the very special ones where your tidally excited modes, G modes inside the star. I think we should call those KOI-54 stars. And the right-hand panel shows you a couple of examples of those. Now, what's interesting about the right-hand panel is these are not snapshots of one segment of data. This is something like several years of data all folded together. And so the little oscillations land on top of themselves over and over and over again. They repeat from orbit to orbit. So this is an example of where the oscillations are in sync with the orbit. There are exact harmonics there. It's not that they're just sine waves with an additional heartbeat on top of it. These are really locked to the orbit. The upper one up top there, that is KOI-54. Okay, let's go to the end then. Next one. Oh, actually, that really was the end. Okay, so that's the title slide I had in the beginning there, and I hope you found some of this entertaining as well as informative. Thanks for your attention.
Do we have any questions?
Yes, from what you said, I think there are some theoretical papers on why AO stars A0 stars would oscillate, but they were not very convincing as far as being able to come up with the period involved, the 11 whatever hours period. Is that where we stand? I mean, I can imagine that one star is oscillating at 11 point whatever it is, the other one is they're very similar stars. Mm-hmm. But what I understand you to say is that the theoretical understanding of an oscillation of that period isn't very convincing.
Yeah, in a nutshell, it's right. There's several complications going on, and it's very hard to untangle whether it's one star or the other or both. My thought is that it's one star. The reason, if it's two stars and one is at the 90th and the other one's at the 91st, then when you go to something like 70th, you should see something right next to it. Every one of those lines should be doubled. But the only one that really looks like it's doubled is the 90th and 91st. So if they were two stars doing very much the same thing, you would see pairs of oscillating spikes in the power spectrum, and you don't see that. The other thing is you can model a light curve with just one star. So if you have one star that's oscillating, you can produce all these modes. You don't need the other star to do it. And so because you don't need the other star to do it, there's no reason to invoke both stars. But I do find it interesting. Why would one star do it and not the other? They're so very similar in mass, temperature, chemical composition. It's very peculiar to me. That I don't think is understood.
And in general, that particular frequency is not well understood. I mean, the fact that it oscillates at 11 hours and whatever can't be understood by just the understanding of an A0 star.
Yes and no. It's not a natural pulsation of an A star. A star would not pulsate anywhere near that frequency. It's much, much too long. But if you were to take an A star and perturb it and just shake it, it would start to ring. And you would ask, well, what frequencies would it ring at? It turns out very much to depend on how you shake the star. So it could be the 90th harmonic, or it could be the 60th harmonic, or any one of those, but it depends on what's the time scale of how you shake the star. It depends on how you excite that mode. So inside the star, there are many, many, many modes, thousands of them. And which one actually turns out to be excited enough that you can see it in the observations, actually see the star get brighter and dimmer in the observation, turns out to simply be which one of those modes is closest to being an exact integer multiple of the orbital period. So if something is a little bit off of the orbital period, just a tiny bit, it won't get excited much. If something is exactly matching the orbital period, it'll resonate and it'll actually grow. The amplitude tends to grow, and you'll get a large pulsation that's visible in the light curve. But if you're off by just a little bit, you get basically nothing. So it's probably pretty much by chance that the 90th and 91st that happen to be the ones that are excited by the orbital period. Now, again, if the orbital period were 27 days, you wouldn't get a 90th and 91st. It'd be another pair somewhere else.
Okay, it looks like opportunity for more theoretical work or something, because it's amazing what they can actually observe with these stars.
Yeah.
Kepler is just amazing. Thank you.
Sure.
Any other questions?
Yeah, I have one elementary question. How in the world did you find out that it was a 90th and 91st? What simple math is there?
Oh, actually, that turns out to be pretty straightforward. So, if you remember the picture of the power spectrum that had those spikes in them, had these two very sharp spikes in them.
Yes.
Those frequencies are now very, very accurate. So basically, you measure where the spike is. And you say, what is the period of that spike? And it turns out that if you take the orbital period of how long does it occur between the brightening events, it's exactly 1/90th of that. And we were kind of led to that. It wasn't a total surprise. We were looking for things that would be orbital harmonics because we were thinking the reason these stars are pulsating has something to do with the two stars going around each other. So there's a natural clock, and we were looking for things that are related to that clock. Now we are obviously expecting things like 1/5 the clock or 1/10. The 191st was a surprise. But it's other these stars turn out to be 241 and that sort of thing. Very, very high order harmonics appear. And I think that's simply because the star wants to oscillate at a certain frequency, but the orbital period is very different from that. Because it's so different, you have to get a very high harmonic. If it was the third harmonic, it'd be much too slow, right? So imagine it's the second harmonic. That's 21 days. The star does not want to do anything at 21 days. But if you go to the 90th harmonic, you're at 11 hours. And the star, 11 hours is perfect for the star. It will ring like crazy. You go a little bit higher and you go to 6 hours, that's too fast. The star doesn't want to ring in 6 hours. So it just turns out to be, the size, the structure of the star, the bigger the star, it's like a resonance cavity. Bigger the object, the size of the object and the density will tell you what frequency it wants to resonate at.
I was thinking about the relationship of harmonics to radio frequencies, and that's just an odd number to come up with.
I agree.
Yeah, okay. Thank you.
Yeah, everyone was surprised, very amused to see the 90th and 91st harmonic there. Yeah. No question about it. There are other heartbeat stars, and the harmonics were like the 10th harmonic. We sort of, there was sort of second, third, fourth, 8th, and 10th harmonics were found. All right, you can imagine those. That makes kind of sense. But this came out of the blue.
Thank you.
I have one question. I got slightly lost in all the numerology of the resonant periods that were not harmonics, saying that what was it, the fifth and the seventh added together gives you the second. Is that saying that those are heterodynes of the other harp? I got lost in all that.
Okay, well, yeah, you're not the only one. No, I think, I don't think that's understood. One of the explanations of is the power that you see in the 90th and 91st harmonic is a lot, right? You know, even though it's less than 1%, that turned out to be quite a lot. That's pretty strong for an oscillation. And so some of that power has difficulty getting out in that mode. And so it turns out it's easier for that power to come out in two other modes. And so they will come out in two other modes, and as long as the sum of the frequencies of those two other modes is the same as the 91st, it works. So it's kind of leakage of power, but in a peculiar nonlinear way.
I see, okay.
Resonant frequency.
Yeah.
Okay, anything else? Well, then let's once again thank Bill Welsh. I found that an absolutely fascinating talk. I hope you all did too. So, thank you.
It's my pleasure.
Thank you.
Well, I truly appreciate that. And as I say to all our speakers, you are now an honorary member of the Big Bear Valley Astronomical Society. And I'm sorry you can't get out of that. And if you're ever up in the Big Bear area, please look us up, and you're welcome to have a tour of the observatory here anytime.
Oh, I like that. Thank you.
Okay. Well, we'll let you go. Thank you so much.
Thank you.
Yeah, thank you.
Okay,
Good night.
see you.
Good night.